Hello, Luigi. Hmm.
So this was a hot subject 20 years ago. I remember you published something. I think I even published something myself. It was a Büttikar. A lot of people trying to compute or measure tunnel time. Hi, Ephraim.
Hello.
Nice meeting you.
How are you?
Nice to meet you. Nice to see you, Michel.
Nice to see you too. So you want to share your screen? Let me, you should be.
Sure. Yes, the option is there. Let me just find the right one. Is it showing up for you?
No.
Not yet. Here
yes.
you are.
Yes.
And we
Okay,
see
you have to be probably in the present.
Yeah. Here you are. That's perfect.
If you want to try animations, you're welcome. But usually it works. This is.
If those don't work, I'm not going to find a way to fix them in the next few minutes. So we'll deal with it.
Okay.
But,
Okay.
that's not a problem.
Yes, you're right to be fatalistic like this, because there's no need to be stressed in this talk. It's better to keep smiling.
Yeah, well, I'm always more concerned about
nowadays.
So thank you for your bio. I had not realized you had worked in the group of Serge Haroche, actually.
Yeah, I spent about a year there. Yeah,
so you were working in their experiments with trapped ions.
I was well, I was connected to the Rydberg work, but I was just as an undergrad working on trying to stabilize lasers for a technique they've never really used for generating circular Rydbergs. It was a much more clever technique than the usual one, but the usual one works just fine. So, you know how it goes in the end. But it was, my first exposure to cavity QED and an exciting time.
Yes. So you actually came back to Paris with as a postdoc with Elisabeth Jacobino.
That's right. Yes, ever since we find every excuse to go back to Paris. A lot of nice groups I enjoy working with there over the years as well.
Yes, fantastic. Yes, we all look forward to your talk. It's you're doing a very interesting experiment. Of course, I am strongly biased for it, but yes, it's always interesting to discuss fundamental quantum mechanics. And I like this quantum archaeology that.
I go back and forth between archaeology.
He even
and
has a
stories.
ichthyosaurus on the screen. So.
Yes.
I forget. I went somewhere to give some talk, and when I asked the cab driver to take me to the university, he said, "Are you here for the conference?" And I didn't even know what conference, but it turns out there was actually an archaeology conference at the same time. And it occurred to me, wait, that's not a bad idea.
Yes. No, it's yeah. We don't go in quantum archaeology. We don't usually go very far in the past, but yes.
Well,
yeah,
I don't know if
this semester I'm doing a special course. I am working with a professor in the humanities, and we give together a class on cinema and physics. And
oh wow,
it's been a lot of fun.
That must be interesting.
Mm.
I was going to say there was a very strange science fiction TV show a year or two ago called Devs. I don't know if you know about it. It's supposed to be about quantum computing.
Mm-hmm.
Well, yeah, they actually do some quantum archaeology, and they go back thousands of years.
Mm-hmm.
Excuse me for interrupting.
Hello, Keith.
Hi, Michelle. How are you?
Good.
Hello.
And yes, the speaker, I'm embarrassed to tell you, I don't know how to pronounce your first name.
I don't think that's embarrassing. It's pronounced Ephraim.
Ephraim. Okay. Thank you very much for agreeing to come, and thank you, Michelle, for making this happen. So I'm looking forward to your talk.
You're welcome. It's a pleasure to. It will be
Thank
a pleasure to introduce Ephraim.
Great, great. Okay, all right.
Yeah. Yeah,
but yes, I remember wondering what your bias would be when where was it, in Trieste, I guess, that I was giving a talk about some of this and you were there, and I was curious to see how you would react. So I was glad to see that you weren't allergic to our version of it, at least.
No, not at all. No, it's I appreciated all your comments, because indeed this question of time in quantum mechanics is always raising questions, since there are no time operator. But I think, like in every quantum measurement experiments, you have to describe the whole measurement system, not just the system and the measurement. What you see is not only a function of the system, but also the way you measure it. It's a sort of a universal quantum quantum situation. But
I like to argue to people that about time, that's even true classically, that we never directly measure time anyway. But I made the mistake of saying that in front of a philosopher a while ago, and he took a lot of issue with what I was saying. So I hope one day to have him teach me how they think about these things.
Yeah, I heard Serge Haroche say one time in a conference that it was a pity that modern cosmology or sophisticated considerations on emergent variables conclude that time doesn't exist, because it is the quantity that we measure the best in physics. So
that's also true.
If it doesn't exist, it's quite a pity. Yes, so we're going to leave people the time to join. I see that Gianluigi Catellani is joining the talk. So Gianluigi is a close colleague of mine. Gianluigi, are you here in person? No, you are. You are not in Leuven.
Okay.
No, I'm in Germany.
We're worried it was just your computer. I see.
Can you hear me?
Yes, we hear you.
Yeah, he's here. He didn't come, right?
No, I'm in Germany. I just, get some of these advertisements still from the department. So this looked interesting.
Well, thank you for coming despite the evening hour. So, by the way, just in terms of timing, then you begin around 4 o'clock or a few minutes after?
Yes, we're going to leave people maybe 2 minutes to come after 4, but I'll start introducing you, and then you have the whole hour to yourself, I guess. We can.
I should aim to finish around 5 or a little earlier.
You know, I would recommend not going too much over time, over the hour, but
Okay.
I think it's also a little bit flexible. And I'm not sure how many questions there will be during your talk. So maybe there will be interruptions. Maybe there will be chat, people writing some chat comments. So we'll see.
Okay, and yeah, I'm fine if people interrupt. I probably won't see the chat on my small screen. So if you happen to see a question you think is worth interrupting me for, go ahead.
I try to follow the chat and relate.
Thank you.
We'll see what how many.
Yeah, it's an interesting new existence this year with its pros and its cons. And some things about these Zoom seminars I think are good, but
yes, you didn't have to travel. It's true that we're missing a lot of interesting discussions, I think. So there's no room for really informal discussions, unfortunately.
Yeah, that is a problem. And the travel, it cuts both ways, right? It's easier to visit many more places without needing the overhead of travel, but at the same time, I miss being able to visit people's labs and actually talk to them about what they're doing in the lab.
Exactly. Exactly. Yeah, so it's now 4, but we're going to wait 2 more minutes.
I'll just stare out at the people in the audience as I would if I were there in person, but now I have to scroll through the audience instead. See 1 or 2 familiar faces or names. Hi, Sharon.
Hey, Ephraim, how's it going?
It's all right.
What's your background there?
That's the Guggenheim.
Ah, oh, that's the circular, yeah, okay. Spiral thing.
Yeah, when I was teaching quantum mechanics last term, I kept looking for themed backgrounds. When I got up to angular momentum, I thought I should find things that would make them dizzy. This was my favorite, so I've kept it.
Got it.
Okay, so I guess we should begin at this point. Thank you everyone for joining in. I feel honored and it's a great pleasure to introduce Aephraim Steinberg, who's professor of physics at the University of Toronto, and whom I have had the pleasure to meet several times. He's also a founding member and past director of the Center for Quantum Information and Quantum Control. And he's also the current director of the CIFAR program in quantum information science, which is an important institution in Canada. And some of us in the United States also are part of this center. So a few words about his bio. Aephraim received his undergraduate degree from Yale University, and he spent a year as a research assistant at the École Normale Supérieure in Serge Haroche's group, before carrying out his PhD on superluminal tunneling with Ray Chow, at the University of California, Berkeley. Then he returned to France and held postdoctoral fellowships at the University of Paris 6 with Elisabeth Jacobino, and he also did a postdoc at what was at NIST with Bill Phillips. Then he went to Toronto, where he's been since 1996. So Aephraim has won several awards, important awards, ranging from the APS Doctoral Thesis Prize in AMO Physics and also a Stacy Fellowship. He's a fellow of the Institute of Physics and of the American Physical Society, the Optical Society of America, and the Royal Society of Canada. So I would like also to mention that he's worked on weak measurement, and his science paper on the average trajectories of single photon in a two-slit interferometer experiment, was selected by Physics World as the breakthrough of 2011. So I'm very happy to welcome him in this online venue and announce his talk, which he will give on the subject of how long does a tunneling particle spend in the forbidden region. And this is an interesting problem in quantum archaeology. So Aephraim, thank you very much again for giving this colloquium, and I leave not the floor, but the screen open to you.
Well, thank you very much for the introduction, Michel, and thank you for the invitation. Thank you all for being here. It's a great pleasure to be back at Yale after all this time, even if only virtually. And it's a particular great honor to hear such a kind introduction from Michel, of all people, as many of you will understand as I get a little further into the talk. Anyway, what I want to describe today is mostly our recent work about tunneling. How long does a tunneling particle spend in the forbidden region? But as I've tried to hint here, there are a few other related problems that are maybe suggested by this cartoon I have in the background. But I really want to make sure to give credit to the people who've done this work. These were heroic experiments that were far more difficult than anything I ever did as a grad student or contemplated doing. And the people who got them done really deserve a huge amount of credit. These tunneling time experiments were led most recently by Raman Ramos, David Spearings, and Isabel Racicot. Ramon is now a postdoc in Barcelona. David has taken over the experiment and is just completing his PhD now, followed up by Joseph McGowan and a few other newer students. Obviously building on work of all of these other people down here. It's been many generations of students building this apparatus up to the level where we were able to do this. And I'll also tell you, if I have time towards the end, of some work on our different apparatus that was led by Josiah Sinclair, who has recently left to start a postdoc in Vladan Vuletich's group, work that's now led by Daniela Angulo-Murcio and Kyle Thompson, with theory help from Aaron Brodich. All right, so let me begin by giving you just a general perspective on why I think these questions are interesting before I go into the details of tunneling times. I think we're all taught conventionally that in quantum mechanics, one can't look at present observations, like where does a particle in a two-slit interferometer hit the screen, and then ask questions about how it got there, about its history. That's, of course, very different from the classical situation where we dig up a bone and we try to draw conclusions about what some dinosaur was doing 65 million years in the past. And what I want to argue, and I want modern physicists to keep in mind, is that there's already something very wrong with this picture, which is the idea that that dinosaur was not a quantum object. And our current understanding of the world is that everything is made up of quantum objects. There is no classical world, and therefore, if I can draw conclusions about what that bone was doing 65 million years ago, I am drawing conclusions about the past of a quantum system. So the real question is, how much can we say about the past of a quantum system. What are the limits? What's the right way to do it? Not simply to say it's impossible to do it at all. So here's a favorite example, and this is one of the examples that's been popularized by Akira Aronoff's group. They've been studying this stuff theoretically for either 30 years or 60 years, depending on where you date the beginnings. And I like to think about it in terms of these guys who stand on street corners or on bridges and try to hoodwink tourists out of their well-earned money by hiding a bill or a coin under one of three boxes. And I think you all know how it goes, right? You put the bill under one box, you move them around, you see if the tourist can guess where it is. And what I want to do is ask you to think about a quantum version of this game, where instead of just putting a coin in box A, B, or C, I tell you, I'm going to put the coin in a superposition of A plus B over root 2. Now, we all know that there's now a 50% probability to find it in A and 50% in B. So to be fair, I'll offer you more information. I'm now going to tell you, suppose I later find the coin after looking for it in a different superposition. I'm going to look for it in B plus C over root 2. If I fail to find it, all bets are off, we reset the game. But if I find it in B plus C over root 2, my question to you is, where was the coin hiding between the preparation and the measurement? And I won't do the experiment right now. It's a little bit of a pain to do it on Zoom. I often do it in person in a colloquium. But I'll tell you the results. I've done this experiment many times. The results are as follows. If I ask a physics audience this question and ask people to raise their hands if they can tell me where the coin was, unless there's someone who has already worked with this particular formalism or with Aronoff, the audience is completely silent. If I ask the same question at a public lecture of an audience of educated non-scientists, there are always people who get what I consider the right answer. And the right answer is as follows. The particle was definitely in B, which we can understand from the process of elimination. I guaranteed that I put it in A or B, so it can't be in C. I guaranteed that I found it in B or C, so it can't be in A, and therefore it must be in B. Now, if we replace those plus symbols with or, right, no one would hesitate. And I think that's what the lay public is doing. But among us physicists, we find it unclear whether we're allowed to do that or not. And yet there's a very definite experimental sense in which this is the right answer. So to me, the moral of the story is that there's something that we don't understand well enough about how to think about quantum mechanics if we're not sure whether or not we can make that substitution. So we need to work on our intuitions, our thinking about quantum mechanics. That's not to say that any calculation you or I could do of a particular outcome for a well-defined experiment is lacking, right? This is a question within the standard formalism of quantum mechanics. We're not overturning any laws of quantum mechanics. We're just trying to develop how we can think about it. So here's the outline of my talk. I'm going to spend a little time just introducing the tunneling time problem, which is a roughly 100-year-old problem now. Talk about our recent experiment published last year on how much time a particle spends in the forbidden region, and then talk about some of our future plans, measuring where exactly particles spend their time while they're tunneling, and what observation does to a quantum system, whether we can actually collapse a system and observe the effects of that collapse. And as I said, I'll at least try to advertise our more recent experiment, which is kind of the opposite. Instead of asking how long does an atom spend in a barrier made of light, I'm going to start asking you how long does a photon spend in an obstacle made of atoms. So here's tunneling. I think this is familiar to all of you, including the cartoon, hopefully. We all learn in undergraduate quantum mechanics that a particle has a finite probability of traversing a region with such high potential energy that classically it would never get across. And we learn how to calculate that probability, which is not very difficult. Most often, we're never asked how long it takes the particle to get across. And that's most definitely not because no physicists ever addressed the problem. If anything, I think it's more because we were so confused by the early attempts to answer this question that pedagogically, we preferred not to raise something we couldn't give a simple answer to. Why can't we give a simple answer? Well, if we think semi-classically, you would argue that as the kinetic energy goes down, gets closer and closer to U naught, the velocity goes down and the time goes up. That would certainly be true. But once E becomes equal to U naught, that semi-classical approximation would diverge. We have a zero kinetic energy, zero velocity, and it would take an infinite amount of time. You probably already suspect that those infinities are usually lifted by a quantum treatment. However, once we get below the barrier, the situation is even worse. E minus U naught is now negative. So if you try to interpret a negative kinetic energy semi-classically, you'd get an imaginary velocity. And generally, we don't even know what to do with that. Now, obviously, that's not the end of the story. You've probably all seen or even carried out simulations like this one, which I stole from Wikipedia. And clearly, we see an incident wave packet approaching a barrier and splitting into a transmitted and a reflected portion. And it would be straightforward to just calculate where is the peak of that transmitted portion compared to the peak of an undisturbed wave packet if we remove the barrier. And the easiest way you might do that would be the stationary phase approximation, right? The way we all learn how to calculate the group delay. And that was done first in the 1930s and then more carefully in the 1950s. And the problem is the stationary phase depends on, well, the transmission phase of this wave packet. And if you look at the way we solve this tunneling problem, what you notice is that propagating waves that behave like e to the ikx accumulate a phase as a function of distance. While inside the barrier, there is no complex exponential, there's just a decaying and a growing exponential with no acquired phase. What that means is that as I increase the thickness of the barrier, the phase at some point stops growing, and the stationary phase time, the group delay, therefore also begins growing. Mathematically, the time delay becomes independent of the thickness of the barrier beyond a certain limit. And the problem there is that if you let the barrier get sufficiently thick, eventually that asymptotic time is smaller than d divided by c. It appears to violate relativity. Now, you might argue, all right, stationary phase is just an approximation. You would be correct. People went beyond that. It's not just a fault in the approximation. You might argue that the Schrodinger equation is non-relativistic, and again, you would be correct. But that's not the reason for this problem. It's been redone with both the Dirac equation and the fully relativistic Maxwell's equations. The same thing occurs. So this seems to be a real prediction of this wave propagation. And it was debated greatly over the course of much of the 20th century, again, starting in the 80s, and finally a bunch of experiments, including my own PhD thesis, but not limited to that, were done in the 1990s to confirm this prediction. That peak really does show up faster than it would if it had been traveling at the speed of light. And that's something often referred to as the Hartmann effect. Here's some early data, but the details there don't matter. I'll take a moment just to say, if this concerns you because you haven't heard about it before, it needn't. It took us a while to understand this, but it does not, in fact, violate relativity. Energy is not traveling faster than light. And one way to understand that is to think about these wave packets, which were meant to be tortoises, but my skills with McDraw turned them into snails. And the idea is that although the peak of the tunneling wave packet may cross some finish line sooner than the peak of an undisturbed and an unslowed wave packet would, a very small fraction of the energy or the probability density actually makes it across. So in fact, at any given time, there's a smaller probability for the particle to have crossed the finish line in the presence of the barrier than in the absence of the barrier. No energy has been accelerated by this. And one way to think about this, a kind of semi-classical optical or electromagnetic picture, would be that what's transmitted really just comes from the leading edge of the incident wave packet and has nothing to do with the peak of the wave packet. Quantum mechanically, that might seem a little strange because since when does a particle know whether it comes from the front or the back of a wave packet? But in some sense, that's what this hints at. Those of you who've thought enough about relativity probably realize we're even more concerned about information than about energy. However, it turns out that no information is traveling faster than light either. All of this can be thought of as a completely causal Green's function. Basically, you can think about the tunnel barrier as carrying out a kind of analog computation, calculating something like a Taylor expansion that's predicting what the wave function should look like a little bit in the future. And as long as the wave packet is narrow band, analytic function that varies slowly enough, that Taylor expansion is incredibly good. So this output wave packet is pretty much indistinguishable from an accelerated copy of the incident wave packet. However, if you went to a larger bandwidth, such as this delta function sketched down here, you'd find that the transmission no longer looks like that. It would instead look like a series of causally retarded copies of that delta function. So these two problems are not there, and that's not going to be the subject of this talk. A lot of this was already understood by many in the 1980s and by most, let's say, in the 1990s. And this led Marcus Büttikar and Rolf Landauer, who I really credit with repopularizing the tunneling time problem in the 1980s, to pioneer different approaches. Basically, they said, we've understood that just looking at the peak of a wave packet is telling us something interesting, but a kind of motion of effects, not the motion of some real physical object. And we should therefore look for other ways to characterize it. And in particular, Rolf wrote this nice column in Nature in the late 80s, distinguishing how long it takes before a particle escapes, like the half-life of a nucleus that decays by alpha decay, and the amount of time the particle spends while escaping inside this narrow tube, as he put it. And he wrote there that the time taken by that final escape event has now been measured in a subtle and definitive experiment by a group at Saclay. And this is why it was such a pleasure to be introduced by Michel, because many of you will notice his name down here. This was really the pioneering measurement of a tunneling time experiment, and the one that was in the back of all of our minds when we started doing these other time delay measurements in the 1990s. And you can look here and recognize perhaps that what you're looking at is the grandfather of today's superconducting qubits. Was this then the end of the story? Was that a definitive and beautiful experiment? Beautiful, most certainly. But if I thought it was definitive, I suppose I wouldn't be here now telling you about this work. And in fact, many of you probably read headlines about 2 years ago claiming that physicists have now solved a great mystery of the quantum world and found that quantum tunneling was so quick that it might in fact be instantaneous. And this is work that built on a new wave of tunneling time measurements started by Ursula Keller's group around 2010, using what she named the Atto clock, looking at the speed of high field ionization, strong field ionization. Overall, I think the lesson that we all got from Büttikar and Landauer is that instead of just asking about the most likely time of arrival of the few particles that get across, if we really want to know how long a particle spends in the tunnel region or how long it interacts with certain objects, we need to think about how we would measure such things. Time is what a clock measures, and the picture that we had here was that if every tunneling particle, represented by Heisenberg hedgehogs here, carried its own little stopwatch, but that stopwatch could be set up to tick only while the particle was inside the barrier. Then we could read off the times on those clocks after the particle had been transmitted. And this was an idea that Büttikar wrote a lot about in 1982, maybe 1983, building on earlier work from Bas and Rybachenko. And I'll spend a moment explaining what their idea was, because it's really the basis for the measurement that we finally did. They imagined that in addition to letting a particle, let's say an electron, tunnel through some barrier, you might let the particle carry a clock hand, like a spin. So an electron is a spin 1/2 particle. We could begin with all the electrons spin polarized along the x direction. And then inside this rectangular barrier, add a magnetic field along the z direction, only in the barrier region. And their idea was that the electrons would now precess in the xy plane only while the electrons were under the barrier. So by reading off the rotation angle after the particles had been transmitted, we could tell how long were they under the influence of that magnetic field, how long were they interacting with the barrier region.
Like an EDM measurement.
Like an EDM measurement. Let me just say there are some relations there, but not exactly. So how did we decide to do that? I don't know how to confine a magnetic field to a region small enough for an electron to tunnel through with significant probability. But starting in the 1990s, we began to think about cooling atoms sufficiently that they would have very long Dupont wavelengths long enough that they could tunnel across barriers made of light. So in particular, we Bose condense a cloud of rubidium-87 atoms, and then we cool them to the point that they have a thermal de Broglie wavelength, or a coherence length of about 4 microns. By contrast, we can make a barrier for them by focusing a blue detuned laser beam around 420 nanometers to about 1 micron. So the width of that barrier is now narrower than their wavelength. We can hope to see significant tunneling. In practice, we actually confine the atoms first to this crossed dipole trap, one beam of which we'll use as a kind of waveguide so that we can really study one-dimensional propagation. Now, the barrier height is determined by the intensity and the detuning of this beam. We lower that to about 150 nanokelvin, which may sound low, but that's much greater than the nanokelvin temperature of the atoms. In fact, it corresponds to an incident velocity on the order of 4 millimeters per second. So if we push these atoms at 4 millimeters per second or more, we expect them to traverse the barrier. Otherwise, we expect them to be reflected. And of course, right in that vicinity, there'll be a transition where some of them quantum tunnel and others are reflected. These are just some pictures showing how we cool the atoms. I don't think I'll go into the details here, but the picture on the right is a time of flight showing that over the course of 60 milliseconds, the radius of our cloud remains unchanged to something on the order of 20 or 30 microns, really showing that they're below 1 nanokelvin. And this movie here shows one of the first times we were able to make a sheet of light act like a barrier. In this case, we actually tried to use gravity to pull the atoms through the barrier. And what you see is an atom cloud spreading out on this table of light until some atoms fall over the edges. Other atoms tunnel through, but the fraction doing that is so small we can't even see it in this image. And you do see the hottest atoms that simply surmount the barrier classically. Remember, we also need this magnetic field. Excuse me. Instead of using a real magnetic field, which it would be difficult to confine to this 1 micron region, we use a different 2-level system as a kind of fictitious spin. So in fact, we use 2 of the ground hyperfine states of rubidium, the F equals 1, M equals 0, and F equals 2, M equals 0 states. These are the states that are used in atomic clocks because of their lack of sensitivity to external perturbations like magnetic fields, which was also very important for us. And now this 2-level system is, of course, mathematically equivalent to a spin. As long as we can couple those 2 states coherently, we can implement exactly what Bass, Rybachenko, and Büttikar had imagined. So we do that using a pair of Raman beams. So we use a 2-photon transition to transfer atoms first up to a virtual state and then back down to the other ground state. In practice, it was already very difficult for us to focus our 420 nanometer beam to 1 micron, let alone make these even smaller probe beams, although we hope to in the future. So instead, for the first experiments, what we did was simply modulate the barrier beam, frequency modulated, at 6.8 gigahertz. So it now has 2 frequency components that are separated by exactly this hyperfine splitting. That's the equivalent in rubidium of the 9 gigahertz definition of the second in a cesium clock, for instance. So here's our experimental sequence. We've Bose condensed and cooled the atoms in a cross-dipole trap. We now remove one of those traps and add a barrier over here near the focus of this horizontal waveguide beam. We use the modulation of that barrier so that as long as the atoms are inside that region, we also get a spin rotation in this fictitious spin space. And then with a magnetic gradient, we push the atoms towards the barrier. Some are transmitted, some are reflected. And by measuring their spins, in principle, we can measure the time that each of these clouds has spent on average interacting with the atoms. So first, of course, we had to calibrate that fictitious magnetic field. On a free wave packet, we see atoms propagate through the barrier, and then we do a Stern-Gerlach experiment to pull them into 2 spatially resolved regions. So these are the original spin along X and the spin along minus